Even though we have more sophisticated ways to treat wastewater before discharging it into streams and rivers, there's one thing that hasn't changed. We still use gravity as the primary way of getting waste to flow away from homes and businesses within the sewers below ground. And eventually we need a way to bring that sewage back up to the surface of the earth. But that's not as easy as it sounds. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about sewage lift stations. This video is sponsored by HelloFresh, America's #1 meal kit. More on them later. I have a video all about the engineering of sewers, and today we're following that wastewater one more step on its smelly journey through a typical city. You can go check out that video after this if you want to learn more, but I'll summarize it quickly here. Most sewers flow by gravity from each home or business toward a wastewater treatment plant. They're installed as pipes, but sewers usually flow only partly full, like smelly water slides or underground creeks and rivers. This is convenient because we don't have to pay a monthly gravity bill, and it almost never gets knocked out during a thunderstorm. It's a free and consistent force that compels sewage downward, but because Earth's gravity only pulls in one direction, sewers must always slope, meaning they often end up well below the ground surface, especially toward their downstream ends. And that can be problematic. Here's why. Sewers are almost always installed in open excavations, also known as trenches. This might seem obvious, but the deeper a trench must be dug, the more difficult, dangerous, disruptive, and ultimately expensive construction becomes. In some cases, it just stops being feasible to chase the slope of a sewer farther and farther below the ground surface. A good alternative is to install a pumping station that can lift raw sewage from its depths back closer to the surface. Lift stations can be small installations designed to handle a few apartment complexes or massive capital projects that pump significant portions of a city's total wastewater flow. A typical lift station consists of a concrete chamber called a wet well. Sewage flows into the wet well by gravity, filling it over time. Once the sewage reaches a prescribed depth, a pump turns on, pushing the wastewater into a specialized sewer pipe called a force main. You always want to keep the liquid moving swiftly in pipes to avoid the solids settling out, so this intermittent operation makes sure that there are no slow trickles during off-peak hours. The sewage travels under pressure within the force main to an uphill manhole where it can continue its journey downward via gravity once again. Another important location for lift stations is at the end of the line. Once wastewater reaches its final destination, there are no magical underground sewage outlets. Septic systems get rid of wastewater through leach fields that infiltrate the subsurface, but they're designed for individual buildings and aren't feasible on a city scale. That would require enormous areas of land to get so much liquid to soak into the soil, not to mention the potential for contamination of the groundwater. Ignoring for now the fact that we need to clean it up first, we still need somewhere for our sewage to go. In most cases, that's a creek, river, or the ocean, meaning we need to lift the sewage up to the surface of the earth one last time. Rather than build wastewater treatment plants in underground layers like stinky superheroes, so we only pump clean water, it's much easier just to lift the raw sewage up to the surface to be treated and eventually discharged. That means we have to send some pretty gross stuff, sewage, through some pretty expensive and sophisticated pieces of machinery, the pumps, and that comes with some challenges. We often think of sewage as its grossest constituents, human excrement. You know, poop. But sewage is a slurry of liquids and solids from a wide variety of sources. Lots of stuff ends up in our wastewater stream, including soil, soap, hair, food, wipes, grease, and trash. These things may make it down the toilet or sink drain and through the plumbing in your house, but in the sewer system they can conglomerate into large balls of grease, rags, and other debris, sometimes called pigtails or fatbergs by wastewater professionals. In addition, with many cities putting efforts into conserving water, the concentration of solids in wastewater is trending upward. Conventional pumps handle liquids just fine, but adding solids in the stream increases the challenge of lifting raw sewage. Let me show you what I mean with this demonstration I set up in my garage. This is a small submersible pump designed for moving water out of basements or pools. It's nothing fancy, just an electric motor with a small impeller inside a molded plastic case. I took off the screen so we can really see how much it can handle. The submersible pump moves clear water just fine. Toilet paper is no issue even for the small pump. It can break apart the paper with no problem. It can even manage small suspended solids like these plastic balls. The particles stay in solution, forming a slurry, similar to raw sewage. However, larger solids in the stream can easily clog the pump. Anything bigger than the spaces in the impeller just won't make it through, and clogging really becomes a problem with stringy debris. These are quote-unquote flushable wipes. They may make it past a toilet, but you can easily see why these type of wipes are a problem in a wastewater stream. I really don't feel like pouring a bunch of grease in my demonstration here, but I'm sure you can imagine how congealed fats and oils would only exacerbate the problem of clogging this pump. It's clear that appropriately sized centrifugal pumps can handle certain types and sizes of suspended solids just fine. Sewage pumps are designed for the extra wear and tear. The impellers have fewer vanes to avoid snags, and the openings are larger so that solids can freely move through them. Different manufacturers have proprietary designs to minimize obstructions to the extent possible, but no sewage pump is clog-proof. Especially with today's concentrated wastewater full of wipes that have been marketed as flushable, clogs in lift stations can be a daily occurrence. Removing a pump, clearing it of debris, and replacing it is a dirty and expensive job, especially if you have to do it frequently. Most lift stations have an alarm when the level gets too high, but if a clog doesn't get cleared fast enough, raw sewage can back up into houses and businesses or overflow the wet well, potentially exposing humans and wildlife to dangerous biohazards. A seemingly obvious solution to the problem of clogging is to use a screen in the lift station wet well to prevent trash from reaching the pumps. But screens have a limitation: they can clog up too. By adding a screen, you've traded pump maintenance for another kind of maintenance, removing and hauling away debris. Smaller lift stations with bar or basket screens can get away with maybe a once-a-week visit from a crew to clean them. Larger pump stations often feature automatic systems that can remove solids from the screen into a dumpster that can be hauled to a landfill every so often. Sometimes using a screen is an effective way to protect against clogging, but it's not always convenient, especially because it creates a separate waste stream to manage. For example, if a lift station is remote where it's inconvenient to send crews for service and maintenance, you might prefer that all the solids remain in the wastewater stream. After all, treatment plants are specifically designed to clean wastewater. They have better equipment and consistent staffing, so it often just makes sense to focus the investments of time and effort at the plant rather than individual lift stations along the way. In these cases, there's another option for minimizing pump clogs: grinding the solids into smaller pieces. There's a nice equivalent to a lift station grinder that can be found under the sinks of many North American homes: the garbage disposal. This common household appliance saves you the trouble and smell of putting food scraps into the wastebasket. It works like a centrifugal pump with a spinning impeller, but it also features a grinding ring consisting of sharp blades and small openings. As the impeller spins the solids, they scrape against the grinding ring, shearing into smaller pieces that can travel through the waste plumbing. My garbage disposal can handle all of the solids I tested with the submersible pump with no issues with clogging. The wipes gave it a little trouble, but it was still able to chew them up. Some lift stations feature grinding pumps that are remarkably similar to under-sink garbage disposals. Others use standalone grinders that simply chew up the solids before they reach the pumps. Grinders are often required at medical facilities and prisons where fibrous solids are more likely to find their way into the wastewater stream. Large grinders are also used where storm drains and sewers are combined because those systems see heavier debris loads from rainwater runoff. A grinder is another expensive piece of equipment to purchase and maintain at a lift station, but it can offer better reliability, fewer clogs, and thus decrease maintenance costs. Of course, clogging is not the only practical challenge of operating a sewage lift station. When you depend on electromechanical equipment to provide an essential service, you always have to plan for things to go wrong. Lift stations usually feature multiple pumps so they can continue operating if one fails. They often have backup generators so that sewage can continue to flow even if grid power is lost. Another issue with lift stations is air bubbles getting into force mains and constricting the flow. Automatic air release valves can purge force mains of these bubbles, but venting sewer gas into populated areas isn't usually a popular prospect. Although our urban lives depend on sewers to carry waste away before it can endanger public health, reminders that they exist are usually unwelcome. Hopefully this video breaks that convention to help you understand a little about the challenges and solutions of managing wastewater to keep your city clean and safe. It's time for everyone's favorite segment of me trying to cook while my wife tries to capture that on video. We're not expert chefs or foodies.
Good evening, engineers, once again. For those who had not joined us, my name is Dennis Nderi. I'm an engineer from Kenya and an engineer at Roads Hub. And I take this opportunity to welcome you to today's meeting. In today's meeting, we'll be covering sewer pump station design. After our previous engagement on waterborne sanitation systems, we saw it wise to continue the conversation further and hold this webinar for you. In today's meeting, we'll be covering oversized sumps that cause septic conditions, pumps that short cycle due to poor level control, raising mains with low velocity and solids buildup, lack of air release points leading to vacuum collapse, and incorrect pump head calculations that waste energy. Before we begin, I would like us to introduce ourselves and get to know each other. I would like to know where we are joining from. So in the chat box, drop the flag of the country you are from. Let's make this interesting. Let's get to know what countries we have present today. Keep them coming, keep them coming. I see we have guys from Uganda, Zimbabwe, Canada, South Africa. South Africa again, Zimbabwe, Somalia. Keep them coming, ladies and gentlemen. Okay, as we keep introducing ourselves in the chat box, I see we have guys from Kenya. I hope my Kenyan brothers and sisters are safe after a day of patriotism yesterday. I feel welcomed, ladies and gentlemen. It's a pleasure to have you today. Okay, keep them coming, keep them coming. We have Ntuku from South Africa. We have Engineer Biron Ochieng from Kenya. It's a pleasure to host you today. The reason why we are holding these webinars is to prepare you for our upcoming course. We have a course on storm and sanitary sewer, which will kick off on 30th June. That's Monday. I'll be sharing the registration link with you guys for whoever is interested. I see Engineer Baron had shared that earlier. You can also go to our website at roadshub.org and then you can purchase your course from there. Our cities are growing, and as they grow, then there raises a concern of how to handle wastewater in these cities. Nairobi, for example, has had a few of these challenges in drainage and wastewater control. And it's upon us as engineers to come together and create solutions to these challenges. I do not want to take any much more of your time because I know you are eager to dive deeper into what this webinar has for you. And I would like to take this opportunity to give you the rules of this webinar. Please stay muted so that we can all interact well. Anytime you feel you have a question to ask, just raise your hand and then we'll give you a chance to speak so that we can all interact in a clear and well manner. Our instructor for today will be Byron Seriant. He's a civil and water engineer from South Africa. He is also an engineer at Roads Hub, particularly as a water and wastewater specialist. He has extensive knowledge in wastewater infrastructure with an experience of over 5 years in this field. Uh, Specifically, he has majored in water reticulation, sewer reticulation, stormwater management, urban roads, bulk water transmission mains, and water treatment plants. He currently works at Vinecraft in Pretoria, South Africa, as a design engineer. And without any much more ado, allow me to introduce Engineer Byron. Engineer Byron, if you can hear us, please take the mic.
All right. Thank you so much, Engineer Derry. Can you hear me? Can you please confirm if I'm audible?
Loud and clear, Engineer.
Thank you so much. Yeah, good evening, everyone. As Engineer Derry has already pointed out, my name is Baron. I just prefer Baron. You don't have to call me engineer. You just Baron. It's well enough for me. So I live and practice engineering in South Africa. That's where I stay. And I'm also part of Roads Up. And today, the idea is to deliver a webinar on sewer pump stations. If you've been with us, you know that we've talked about sanitary sewer, predominantly covering the conventional gravity sewer designs. And we've done a course in that. I believe the last webinar that we had, I believe it was 2 to 3 weeks ago, we were talking about the types of sanitation. So we did speak about, if my memory serves me well, we spoke about conventional gravity sewers, shallow sewers, vacuum sewers, and small bore sewers. Yeah, I remember. So those are the four that we covered. But as you know, when you're dealing with wastewater, it's a very big sector. There's a lot of technologies for you to master and for you to learn. So today we're going to be covering one of them that you're probably going to encounter in the field, which is your sewer pump stations. So it's more of a hybrid from your gravity sewers, but then you would have to add something to your system so that it can function accordingly. So we're going to be talking extensively on that. What are the components that are involved in a sewer pump station? So yeah, Engineer Ndere has already shared a link as well in the chat box. You can just visit our website so that you can check the number of courses that we are providing. So we've got a number of courses that are actually coming up. So the first one, the most recent one, is your sanitary sewer. We are going to be dealing with gravity sewers and a little bit of pump station design in detail. So much of what we're going to cover today is going to be an introduction, and a lot more details also going to be covered in the course. So do check it out. You can go to our website. The course is starting on the 30th of June. So that's your Monday. I believe soon after that, we're having actually 2 courses that are running this coming July. We've got structural modeling in Revit. So do check that one out. I believe it's starting on the 16th of July. Then we also have highway design in Civil 3D. It's also starting sometime in July. I believe it's 16 July, if I'm not mistaken in the dates. So you can just quickly click on the link that you're seeing in the chat box just to confirm on the dates. But these are the number of courses that we're having, and you can just enroll on the course that you like to enroll to. So yeah, guys, thank you so much for joining. Really appreciate you. So what we're going to do, as you can see, I've turned my camera on so that you guys can see who you're talking to. It's quite cold where I am. That's why I'm wearing a jersey like this. I'm feeling very cold and my office is very cold. So I'm not so sure where you guys are joining us from. In my country, it's winter at the moment. So I would like to set some ground rules before we start. First of all, the session is going to be recorded. So rest assured, you're going to get the recording. If you're part of our WhatsApp community group, the recording will be shared. You can also check out Rosa on all the social media platforms. We are there on YouTube. Make sure that you subscribe and you turn on notification bell on so that you can always receive notifications when we post a new videos. There is always a webinar that's happening. Yesterday, there was contracts and claims. I don't know if you guys attended that one. It's amazing knowledge. I hope you guys do check that one out. We do have a series for that one. So the videos are also there on Facebook, and particularly YouTube. That's actually my favorite as well. So do subscribe, turn on your notification bell, and also just check on your website as well. We also have all these free webinars there, so that you can check them out. So there's someone who keeps requesting to record it on their computer, and yeah, I keep declining. You do have access to this, so you can just check them out there. So the recording will be provided for you free of charge, of course. That's the first one. The second one, please ensure that you mute your mic, because the section is going to be recorded, like I said. So we do not want to disturb some people that come. We also don't want to disturb the flow of the session, right? So maybe I'm in the middle of something, then you start speaking or you ask something, it can distract the instructor. So should you have questions, which I'll probably stop every 30 minutes of presentation so that I can just check in the chat box. Should you have questions, please drop them in the chat box. I promise you, I will look at them. I will look at them. I'll probably leave like 10 to 15 minutes at the end of this session so that I can just go through the questions. Much of the knowledge gets shared during the feedback session. So if you have the questions, just drop them in the chat box. Resist the urge of unmuting your mic and speaking over the instructor. Yeah, I think that's the only ground rules that we have. So without wasting much of your time, let's get right into it. So I'm just going to switch off my camera and then we can start. CPO in the chat box is saying, please share the WhatsApp channel in the chat. Engineer Derek, can you do that for us? He's probably going to share the WhatsApp link on the chat box so that you can just click and join that one. All right. So I'll just quickly share my screen. Please confirm if you can see my screen. Can you guys see my screen? You can drop a one in the chat box if you can see my screen. Thank you, thank you, thank you. All right, I can see all the ones. Let me just check. Ones. Lance, Wesley, thank you. Jackson, it's good to see you. Thank you so much for joining us. I remember you. Trevor, thank you so much. Wesley dropped it too, but that's fine. Thank you so much. I get the message. So yeah, if you guys can see my screen, then that's good. So today we're talking about the sewer substation design. The sewer substation design. So as you can see, so the topics to be covered. First of all, we're just going to talk about the purpose of the sewer pump station. Why? Why do we need the pump station, and in what circumstances is it applicable? So you need to understand under what circumstances do you use a sewer pump station. You just don't use it because you want to use it, right? The moment we introduce the word pump, just know that there's a lot of electricity that is involved. I'm sure you guys understand that. And the moment you also introduce a pump, know that there's a lot of O&M that goes into that operation. That O&M means operation and management. So it's also something that you would be forced to think about. So yeah, the purpose of a sewer pump station. Then we're also going to touch on the sump design, which is also known as a wet well, depending on which manual you read. But in most of the manuals that I've read, they just refer to it as a sump, but some they say it's a wet well, so it's one of the two. Then we're also going to briefly talk about pump sizing. Now, I realize that this is something that is mostly relegated to the mechanical engineers. And what then happens usually is I've noticed that there are pump stations that are usually oversized, right? And I remember when I was like just starting in design, you would get away with oversizing everything, so that you are like, okay, I just want to oversize just in case it just works. But there is a danger as well in oversizing. Let me just say this. Anything that involves water hydraulics or wastewater management, as long as there is water involved, if you oversize your infrastructure, it will affect the efficiency. of that operation of that infrastructure. It's different from, let's say, maybe you're doing like structural design. You can oversize a beam, right? Exceed the safety factor, the factor of safety, I mean, and you can still get away with it. Or instead of putting Y20s, you put Y32s, your reinforcement bars. But in water hydraulics, the moment you oversize a pump, the moment you oversize a pipe, there is a direct effect that it will have on the functionality of that system. So we don't always want to oversize. And I've seen a lot of pumps that have been oversized. Obviously, people won't undersize, because if you undersize, the evidence is quite clear. We can actually see that this thing has been undersized. So there is an obvious danger in oversizing some of this. Then we're also going to talk about the rising main. So yeah, we're starting on the sump, then we'll talk about the pump, then we'll talk about the rising main. So I'll try and increase my speed because we do have a lot of content to cover. And I also want to leave some time so that we can get to answer a few questions and discuss as we go. Right. Why is sewer pump station? Now, I believe some of you guys that came early when you were watching the video that we're just watching, why would you need a sewer pump station or a wet well? What's the purpose of it, right? First things first, you have to understand that it is part of wastewater collection system, right? Its main purpose is to move wastewater from lower elevations to higher elevations when gravity flow alone is not sufficient, right? So we need to emphasize on this part. Its main purpose is to move wastewater from lower elevations to higher elevations when gravity alone is not sufficient. So remember, sewers utilize gravity to collect and transport wastewater. Now, I did mention this, that predominantly we'll be focusing on your conventional gravity sewers, right? So as you know, you just have your pipes that are laid at a slope, right? So we take advantage of the gravity, so that water is just probably going to flow and collect at one point, then transported by trunk sewer probably to a wastewater treatment plant. Now, what happens in an event where you cannot use gravity, right? That's the question that we're talking about, because you're not always going to design your sewer system in a place where you have slope to your advantage. So let me just quickly sketch something here. There's something that I noticed. I was actually working on a project somewhere here in this country. So let's say we have a terrain. I hope you guys can see what I'm trying to draw. Let me try and use a red color. It's quite visible. So in this terrain, okay, that's a bit big. Let me just use red there. So in this terrain, what happens is this is just a place, right? Let's just think of this as a place. There are houses all over this place, right? Now, what was happening is that we had a treatment plant. Now, the plant that we had was over this side. So obviously, the most sensible thing to do is then to figure out our slope and then design a gravity sewer line, probably a trunk sewer line that will transport all your sewage from this area, collect all the sewage from this area, taking it to the wastewater treatment plant. Now, the problem that we're having is that this area had two drainage points. By two drainage points, this is what I mean. I would just approximately cut it into half. The first side, like this side, which I'm going to call A, all the water was concentrating at this point X, right? Then this side B, all the wastewater was concentrating at this point Y, right? Like it was sloping. Like if I'm to draw this, maybe the cross-sectional view, it would be something like this, right? So this is where your X is and this is where your Y is. So the slope on the A side, like the catchment area, the catchment A, right? The slope was collecting at this particular point. So it was sloping in this direction, right? Where my arrow is. Then for the catchment B, it was sloping on the other side, right? But now the problem that we're having is we don't have another wastewater treatment plant this side. The only wastewater treatment plant we have is on the other side. How then do you move this sewer and take it all the way this side? You see, so in a situation like this, depending on how big the problem is or how big the project is, we might need to have a sump, right? We would have to design a pump station because we cannot utilize gravity to move this wastewater all the way this side. Actually, we can, but then it would have us excavate manholes that are 10 meters deep, and that's not practical at all. Anything below 3 meters for me becomes extremely dangerous. As you know, I always like to have all my manhole layers to be at most 1.5 meters all the time, all the time. But you do get instances where you go up to 2 meters. If you want to know, 2 meters is very deep. If you've ever been to site and you've seen these pipes being laid, 2 meters is extremely deep. Like if you're in a room, just look at the door in your house. That's approximately 2 meters. So imagine trenching that deep just to lay a pipe. So don't play with 2 meters. Now, if we are having a situation like this where you have to trench anything greater than 3 meters up to 10 meters, it just becomes a non-starter. Right? It becomes extremely expensive and it's extremely difficult. And the safety as well of you working at such depth, it becomes very, very difficult and very dangerous. So in instances like this where you cannot utilize the concept of gravity, where you need to pump your sewer or your sewage or your wastewater to a place where you can utilize your slopes and gravity, that's where we have to employ a sump station, right? So a sump station would have to have a collection point. So this is where we're going to collect the sewer. Then once we collect the sewer, then we pump that sewer, right? So we're going to design a collection system, right? I remember when I was in college, there's this lady called Dr. Shinyama. She's the one who taught me, wastewater engineering. She was a doctor. So one day she shows up to class. She's like, "What is design?" And we start, bringing these big terms and definitions. And she really simplified it. Design is simply giving something shape and size, right? So if I say we want to design a sump today we want to size a sump and we want to give it a shape, right? So either we're going to do a cylindrical wet well or we're going to do a rectangular wet well. It's up to us, but we have to state the parameters and we have to size it properly. So if we make it too big, we obviously have problems. Now, remember one thing that I said, whenever you're working with water hydraulics, never, never, never oversize your infrastructure. It defeats the entire efficiency of how it's supposed to function. Never oversize them. You never get away with oversizing stuff, particularly if you're dealing with water. Okay, so we want to give this thing a shape and we want to give this thing a size. There are dangers, of course, of oversizing it. So we are going to have to size our sump, which is the collection, because this soil has to be collected in a certain infrastructure. Then after it has been collected, then it has to be pumped, right? Then we have to size the pump. After we pump it, it's going to be transported in a rising main, which is a pipeline. Then we also have to design and size that pipeline. So there's a lot of thought and a lot of mathematics that is going to go into this. So yeah, sit back, relax, and just get your calculators out. We're going to be calculating a lot. So I think we've established that fact that saying the main purpose of a sump, right, is to move wastewater from lower elevations to high elevations when gravity flow alone is not sufficient. So when gravity is not on your side, think pump station, right? And another issue again, or another scenario where you can use a pump station, sorry, is when you're having or you're laying a sewer in a very flat terrain, right? Like there are areas where it's extremely flat. There is no slope, so the ground is not sloping to anywhere, to any direction. In those instances, you would have to use a pump station, because what then happens is that, remember, think about this. Sewer, gravity. Just think about gravity. The moment you talk sanitary sewer, the first thing that should come into your mind, gravity and slope, right? So picture this. You're having a very flat terrain like that, and you want to lay your pipes. Let me just get a different color. Blue, I think, would work. So this will probably be my first manhole, right? Remember, all your first manhole should have a minimum of 0.75 meters, right? This is the minimum. Your first manholes, all first manholes, so that you can be able to connect from the inside house with a slope of 1:60. So now I have my first manhole, and according to my manuals, what is the minimum slope that we can have? Depending on the manual, but the minimum slope that you can go at is 1:6, 1:200 for a minimum pipe diameter of 150, right? In some countries, they use minimum pipe diameter of 160. So let's just say we are having a minimum pipe diameter of what? Of 160. So if we're to maintain a slope of 1:200, you see, if I'm to maintain that slope, I'll continue going. And the further I go downstream, right, the deeper I have to trench for me to be able to lay that pipe. Because as you can see now, my ground is extremely straight, right? Or flat, let me put it that way. This ground is extremely flat. It's not sloping, or it's not going to the direction of my sewer. So I'm trying to run away from, remember, I said anything greater than 3 meters. This is just my professional advice, but some manuals, they say 3.5, you can go 8 to 3.5, but anything greater than 3.5, it becomes extremely dangerous and expensive to continue trenching. So say you have to maintain, because whenever you're doing a sewer, you're laying your pipes, remember we are utilizing slope. So your pipes have to be at a minimum slope. So I'm using the most minimum slope we can, right? 1:200. It's relatively gentle, right? But eventually, if you're working with a flat terrain, there's gonna come a time where you're going to have your depth X here greater than 3.5. And if you continue going downstream, you're probably going to be increasing that depth of trenching. I'm sure you guys understand the concept, right? So in a situation like this, you would probably have to interrupt your rising main, and let's say you install a wet well here. So you're saying your pipes will come and then they pour water into that. They pour your sewage into that wet well, then you connect your pumps there, then you then pump your sewage, taking it further. So those are the two conditions that you should be able to think about having a sewer pump station. Now, this is the last resort. Please let me say this, and I say this once again. This is the last resort, right? We never like to design sewer pump stations, right? This should be your last resort when you're like, okay, fine, we do not have any options. You should. That's why I always encourage people to do a slope analysis. So you get your surface from your surveyor. You have to analyze your slope and understand your catchment areas. How is this thing draining, right? I was actually having a conversation with a friend this other time, and we were reviewing this project that was done, and it was extremely expensive because this gentleman, they just found a slope and they just started going with it, and they had a manhole that was as deep as 10 meters, and this thing was approved and it was supposed to be constructed. And then we were just like, no, listen, we need to come up with something better. You know what I mean? Then we had to do a slope analysis. Of course, you have to do a lot of rerouting. This is where the sewer design comes in. You have to do a lot of rerouting to find the best way you can lay your pipes at minimum trenching depth, right? So it turns out we didn't have to dig that deep, right? And we also didn't have to use the pump station, because the moment you also introduce a pump station, like I said earlier, there is an operation and maintenance that is involved. There's the cost of electricity. Like in my country right now, I think approximately electricity is like 220 cents per kilowatt, right? So let's say you are having a pump motor, which is like 50 kilowatts. So you can do the mathematics and you see, okay, how much electricity am I going to be consuming an hour? So how much money do I need to be paying for this thing an hour? And for how long does this thing has to be running, right? Particularly for your pump station, it has a maximum of about 6 starts per hour, right? So which means it's going to be running approximately 10 to 15 minutes per hour. So you add that up and you see how many hours are you going to have in a day. So you see that it becomes something that is very, very expensive. So it should be our last resort when we have no option at all to deal with wastewater management. We don't have any other option. We have to deal with this waste. And usually when we involve a pump station, it has to be worth it. Let's say you're dealing with a large quantities of sewer. It can't be 200 houses and then you say let's have a pump station. Like economically, it does not make sense. Even as an engineer, you can literally understand, like especially when you calculate your dry weather flows for 200 households and you see, can you justify having a pump station for 200 households, right? As long as you can economically justify your solution, then that should make sense, right? Another thing as an engineer, you also have to know that you're only not talking about efficiency, but there's also the economics of whatever you're designing. It has to make sense. It's pointless for you to design infrastructure that cannot be implemented because it's extremely expensive. So I just wanted to put it out there. Yes, we're talking about it today, but this should be our last resort. Okay, so those are the two options that you should consider having a sump station. Somebody's writing on my screen. I don't know who that is. Please stop. Great, right? So we already spoke about this. Sewer pump stations or lift stations, called a lift station as well. What is the first thing is to overcome topography, save low-lying areas, reduce deep excavation, transfer wastewater between zones. So this is what I was saying. Like, you can see this picture that you're looking at, right? This is more of a flat terrain. So you see that this sewer is coming from this direction, right, at a certain slope, right? Then it collects in a sump, right? Then in the sump, these are called submersible pumps. We're going to talk about it as we start talking about pump. Then that sewer is going to collect in this sump, right? Then after 10 to 15 minutes, depending on the cycling time that we would have designed that sump, then our pumps, they turn on, then they pump that sewer, then it goes up, right? So these are the four circumstances. Why do we use a lift station? To overcome topography, to save low-lying areas, this is your flat terrains, to reduce deep excavation, and to transfer wastewater between zones. Now, case in point, in coastal areas with flat terrain, wastewater from homes and businesses cannot flow easily to the treatment plant. Instead of installing deep and expensive sewer system, which is your gravity sewers, engineers shall install a sewage pump to lift the sewage to a higher level. Right. So there are some instances where we cannot utilize gravity alone. So in those instances, we would have to ensure that we have got a lift station, right? Okay, that's good. So this is a typical lift station. As you can see, this is a submersible pump, right? This is the best picture that I could find. I don't know if there's anyone who's ever seen one, but I've seen quite a number. It's not a very good sight, especially if you've seen that one that has been working and is being maintained. Yeah, but it looks something like this. So I'm going to show you a couple of pictures that we're going to be looking at. Now, look at this picture here that we're looking at on the right. It's a typical sump station. So before maybe I start explaining what's happening, let me explain the image that you're looking at. So this is a typical, I took this from Van Vuren. He's a doctor in wastewater management from South Africa. So this is something that I took from their book. Now, as you can see, this is your pump house on the left. So this is a pump house, as you can see, right? Your pump house there, this is what we call a self-priming pump, right? As you can see, this is what we call the suction header, right? The suction pipe, right? As you can see here. Then on the other side, we are having a sump. So we want to start by designing this thing here, the sump. And as you can see from this side, your sewage will be coming from this side, collecting in your sump. Then it's going to be sucked in by the pump, which is a self-priming pump. Then it is going to be pumped out, right? So this is the delivery pipe. This is the suction pipe here, right? This is how it looks like. This is a typical pump station, right? This one utilizes what we're calling a self-priming pump, right? So the first thing that you need to understand if you are designing a wet well, right? The first thing is its storage capacity, right? What should it do? The first thing is it should provide sufficient storage for pump operation cycles. It should provide sufficient storage for pump operation cycles. So the first thing is it has to be able to contain that sewage that that is expecting. So what do we mean by that first point? You have to know how much sewage are you going to be collecting and how much sewage you're going to be expecting, right? So what that means, first of all, is we need to know the volumes, right? So we have to definitely calculate the volumes, right? So I usually tell people that here we use what we call the ADWF, which is your average dry weather flow. You don't use your peak flows. Do not use your peak flows. You use your the average daily dry weather flow. So some manuals they have it as ADD, it always confuses me. Some manuals they use it as ADDWF. Some manuals, they just write it as ADWF, right? Which is your average daily dry weather flow or your average dry weather flow. So providing sufficient storage for the pump operation. So how do we know the volume that's coming? We are working with our ADWF. So we have to know what is the average flow that's coming in. Remember, we also talk about this whenever we're designing our sewer, to say before we even start sizing any pipes, right, we need to understand what is the flow, the average flow that we're going to be expecting, right? So it's the flow that is going to be coming in the houses, right? First of all, we make an assumption depending on the manual, how much water is being consumed by each house. Then we use the return flow method, right? So at this particular moment, listen, you do not have to use peak factors. You use the ATF only, right? You're going to see why I use it this way. The moment you use the ATI, the peak dry weather flow, what you do is you oversize your sump. So I'm just putting it out there. NB, use the ADWF now. The second point when you're considering, these are design consideration for your sump, to prevent sedimentation and auto issues. Right? How do you prevent your sedimentation in your sump? Your sump has to have what we call a self-cleansing capacity. So which means there is a ramp that must be constructed within your pump, your sump, sorry. There's a ramp that must be constructed within your sump. Because you're going to see different types, but this ramp is usually between 45 degrees and 60 degrees. I prefer using 60 degrees. So we need a self-cleansing ramp, right? So this is to ensure that all the solids, they gradually come and build up at this suction header here, right? So there is no sump that does not have a self-cleansing capacity. It must have it must have a benching or a ramp in it to ensure that there is no sedimentation. Because if you don't have this, you probably have a tendency of sediments that will probably settle at the furthest part of that sump, which is probably further away from your suction header, right? And you do not want that, right? So your sump must have to prevent sedimentation and auto issues. Now, for the auto issues, we're probably going to cover that on this third point: prevent formation of septic conditions and autos. So a maximum of 30 minutes retention time at an average design flows will be allowed. So what does this mean? You know that sewage, if you keep it long enough in a closed environment, particularly in our country, because our country is quite warm, right? Just give it maybe at least a few hours, it will develop septic conditions, right? So you need to ensure that you avoid septic conditions in your pipe, right? So what are septic conditions? Maybe somebody might be asking, you know what a septic tank is, right? So septic conditions is more of like, this is where your anaerobic bacteria takes over, right? Then there's that decomposition that releases that foul gas called hydrogen sulfide, right? I'm sure you've been through like a pump station or maybe a place where there's like a sewer spillage. You know, that smell, that sounds like a rotten egg, right? It's a foul smell, sounds like a rotten egg, right? So that gas is very corrosive, just so you guys know, and it's very toxic, right? So we are trying to ensure that when we design our wet well, it does not have septic conditions. So we do not have to keep our sewer in that wet well for a very long time. Now, there are design standards to this. Now, we have got what we call a maximum time for retention, right? There's a retention period that you have to take into consideration when you're sizing this thing. So depending on the manuals that you're using, right, or depending on the design that you're using, right? So you have between 10 to 30 minutes. So usually this is how it works. The first retention, so you might say my retention time, it starts, we have 10, we have 15, we have 20, 25, then 30. So when you design your sump, you're already making that provision to say, okay, fine. Remember, I'm only allowed to keep this sewage in this wet well for specified period of time. I can't keep it for very long so that I don't have septic conditions. So your retention time, you then get to choose what retention time you want to use. I usually like to use a maximum of 30 minutes per retention time, right? So what this means is that every 30 minutes of collecting your sewer in this infrastructure, your pump will switch on and it will start pumping, or it will start sucking that wastewater and pumping it out, right? It will start sucking that wastewater and pumping out, right? So 30 minutes, then it sucks all the wastewater out, then it switches off, obviously, when it reaches a certain level, right? Then it collects again for another 30 minutes, then your pump switches on. So one thing that you would have to understand, that I'm sure you are noticing where I'm going with this. When you're designing a wet well, your pump is not pumping 24/7, or it's not pumping continuously like you would do maybe when you're designing a booster pump station or your water pump station where you're pumping potable water, right? You're not pumping, say, maybe for 10 straight hours. Here you've got what we call cycling times. So we pump per cycle. So the retention time, if it's 30 minutes, then your pump will probably pump until it finishes the water in that sump, the wastewater, I mean, then it switches off. There is usually sensors, switches off. Then we collect the wastewater again for another 30 minutes, then your pump switches on, right? So you need to know these retention times, and you can choose whichever retention time you're going to use, right? So you can use any time from 10 minutes up to 30 minutes. I like to use 30 minutes because I don't want my pump to be always starting a lot. So usually in some designs, if you use a retention time of 10 minutes, or if you use a lower retention time, that's 10 or 15 minutes, your pump would have to cycle a lot more within an hour. So check this. If I'm using 30 minutes retention time, right, it simply means the maximum starts that I have to start my pump in an hour, it's twice only, which means I have to start my pump only twice within an hour for it to be continuously emptying my septic, my wet well, and pumping the sewage out. But if I'm having, say, a retention time of 10 minutes or a retention time of 15 minutes for that matter, which means my maximum starts will probably be what? Be 4 times. So which means my pump would have to be switched on and off, switched on and off, switched on and off, switched on and off for 4 times, right? Then if I'm having a retention time of 10 minutes, which means it's 6 times. I'm sure you guys get that. So I usually like to go for the maximum retention time. I've got my own reasons as well, but I usually like to go for the maximum retention time. You can always play around with these figures and see which design retention time works ideal for you, right? So that's that. So we've covered that part. So that's quite important. So I've got a design criteria that I've used. This is a snippet from a design that I was working on, right? So I usually just have a design criteria. So what is the design horizon? Is it full development? We were designing for 2,411 stands, right? So we're collecting sewer from 2,411 stands, right? That's good. So what are our design flows? So we know that our ADF will be A multiplied by 0.85, which is our return flow. So what is A? A is actually the average daily flow, right? Then we have our peak dry weather flow, right? We use a peak factor of 2.0. In some manuals, and some people can use 2.5. I use a more conservative peak factor, a 2.0. Then we have to also allow for stormwater ingress, which is your peak wet weather flow, right? It's 15%. Now, there's some designs that are quite extreme that go up to 30% of stormwater infiltration, right? So these are things that you also have to just think about. Just don't place figures haphazardly. You need to know why you're using the factors that you're using, right? We usually talk about this in detail when we do gravity designs, right? Then after that, we come to a waterborne sanitation design. Like, this is the formula for calculating the sump size, right? Remember, we said we want to design a sump, right? So what do we design? We want to design something, we want to give it shape and size. So we have to size this thing. You just don't approximate to say, okay, I'm servicing 2,000 houses, so my sump will be 3 meters deep. 4 meters wide and 6 meters long. That's not how it works. We need the proper size, because if you oversize it, there's a chance that your wastewater will develop septic conditions, or your pump will actually cavitate, because all that you will probably be collecting a lot more sewer, right? And not all of the sewer will be pumped out of your sump. So some sewer will stay in the sump, right? Generally creating septic conditions. So we're trying to run away from septic conditions. So should you oversize your sump, you're probably going to have a problem with septic conditions. And septic conditions, they lead to odorous gases being released. So that's your hydrogen sulfide. They're quite corrosive and they're quite poisonous. So this is the formula that we use, right? It's obviously taken from the sanitation design manual. You can also confirm with the CSIR manuals as well. This is the formula that we use. So let me just quickly explain what you're looking at. So you've got VA, which is the required wet well, right? So VA over Q is the required wet well. Then you've got T. T is the minimum time in minutes of one pumping cycle. Then we've got QP. Then you've got VT. So whenever you design a sump, you always have to design what we call a storage, an emergency storage pond, right? You always have to design an emergency storage pond, right? This is per the manual. This is the standard practice, right? Should anything happen to your pump station, or let's say there's a breakdown or there's a power outage, your sewer pump station should have a capacity to be able to store an emergency flow. So you should always design for emergency storage. So the emergency storage is usually calculated by that formula. The V is equals to Q multiplied by TE, where your TE is your minimum emergency storage time, usually from 4 to 6 hours. Then you've got your Q, which is the average raw sewage inflow rate, right, which is your ADDWF, right? Okay, let me just quickly check in the chat box if we have got any questions. Just a moment. Okay, it's almost 7 o'clock now. Just quickly answer those questions in the next 15 minutes, right? So what you then do here, it's quite easy. T, we already spoke about T. T is your minimum time in minutes. T is your minimum time in minutes. T is your minimum time in minutes. Then VA, like we said, is the required wet well capacity in cubic meters per second. Please take note of your units. So what you then do there, it's quite simple. You just make your VA the subject of the formula and you bring everything that side. So your T, remember we said before you even start doing the design, you have to figure out what is your T. So we said you can choose between 10 to 30 minutes, right? So if your T, I will probably use T is 30 minutes, right? So your T will be 30 minutes. Then your QP, which is your pumping rate, right? Let's go to the next page. What is your QP, right? So the capacity of the pumping station should be equal or exceed the instantaneous peak wet weather flow, which is your IPWWF, or which is just your peak wet weather flow, right? That arrives at the pumping station to allow for stormwater ingress. In the case of a 30% stormwater allowance, the pump should have a capacity equal to the design flow or generally given by that formula. So your QP should be 1.43 multiplied by your peak wet weather flow. Right. So this QP here, the pumping rate, you guys should understand this. Your pumping rate should be significantly higher than the incoming sewage flow, right? So this is your calculator Q with the subscript P, right? We are saying it's given by this formula where you're saying 1.43 multiplied by IPDWF, which is also your peak wet weather flow, right? So you can use 1.43, or you can just take your peak wet weather flow from your sewage calculations and use that figure. I'm just going to show you just now. So that's the formula that you use, right? So this is actually taken from a proper design. So let me explain this. So this is a typical hydraulic design that we are probably going to be looking at in depth in our course. So the 8 DWF, this is the figure that I'm talking about, right? So we are simply saying for this particular housing stance, we are probably going to be expecting this is the figure that I'm looking at down here, 3.357 liters per second, right? Then I've got my peak dry weather flow with a peak factor of 2.0. So that's what we're having there for my peak flows, right? Then my peak wet weather flow with a peak factor of 15%, that's 1.15, that's your storm water increase, right? Then you are having what? 7.72. So you can use this one. This is what this question is saying, or this statement is saying, right? The capacity of the pumping station should be equal or exceed the instantaneous peak wet weather flow. So I can use my pumping rate as the peak wet weather flow, right? I can use my pumping rate as what? The peak wet weather flow. So for this thing to function very well, we are simply saying the Q that is required to be pumped by my pump station should be at least 7.72 liters per second. While it's the incoming Q, remember, you do not use the peak dry weather flow. You use the 8 DWF, which is the average dry weather flow. Your Q small should be 3.37. I hope you guys understand that. Alternatively, you just multiply this by 1.43. That also significantly increases the size of your wet well. So once you have all those figures, you just plug and play. You have in your T is 30 minutes, right? You have in your Q is we said it's 3.37, I believe, liters per second. You have in your big Q, which is 7.72 liters per second. You have in your Q small. So what you can do here is just making V the subject of formula. Now, one thing that I've noticed, especially I'm sure you guys are I would want you to experiment with this formula, is you need to be very careful when you're calculating with your units. Make sure that your units are homogeneous. One simple mistake here with converting your units, you'll get values that are unrealistic, right? You'll definitely get values that are unrealistic, right? So this is the formula. It's quite simple. You just do plug and play. So that's why I had to spend so much time emphasizing on the fact that which Q do you use and which big Q do you use. So you have to select between these two, and you have to ensure that you make the right choice, right? Okay, so that's your Q. So these are the design flows that we have and all that stuff, right? So here's the example. Thank God I actually brought an example that I actually did calculate it, right? So what are we saying, right? So we are simply saying QP. I decided to then go with this formula of multiplying my QP with 1.43. That's a mistake there. It's supposed to be 1.43, not 14.43. So what's going to happen is my peak wet weather flow, which is by 7.72, right? This one, as you can see, my 7.72. Then I get my QP, which is the discharge that I want for this wet well. So it's 11.0396 liters per second. What is my Q? My Q is that small letter Q there. What is my small letter Q, which is the ADWF, right? ADWF is 3.357, right? There you go, 3.357. There you go. So my pumping rate is that one, right? So as you can see, ensure that your units are homogeneous. So at the end of the day, I want to calculate the volume of this thing. So everything has to be in meters per something. So as you can see, I had to convert my QP from liters per second to cubic meters per second. Same applies with your inflow rate, which is 3.357 liters per second. You convert it to your cubic meters per second. Now remember, I selected a maximum of 30 minutes, which is 2 maximum starts per hour, right? So this is just a design example, 2 maximum starts per hour. Then using that formula, I just simply made V the subject of the formula. It's quite easy, right? This is what you get. V is equals to big T over 1 over Q minus 1 all over big Q minus small q. You just plug and play. Now T, I want you guys to notice this. Everything is in cubic meters per second, like the inflow is in cubic meters per second. And I'm saying my T is 30 minutes, so I have to convert 30 minutes to seconds. Remember, always ensure that your units are homogeneous. Then you just plug and play. You're going to get your V as 10.73 cubic meters. So you can just round it up. Then you have in your VA as 11 cubic meters. So what are the dimensions that you're going to propose for your sump. You know that your sump is going to have a total volume of 11 cubic meters. How then do you size your sump? Right, so you can literally say, okay, I'm just going to hold my depth constant, because I usually like to have a minimum depth of a maximum depth of 2 meters, right? So I select a maximum depth of 2 meters, right? Then if I hold my maximum depth at 2 meters, so you're just saying L times W times an H of 2 meters is equals to 11 cubic meters. Then you just plug and play. You use maximum and minimum to find the maximum dimensions of your proposed sum details. So as you can see, if I multiply my length 3.32, then my width of 2 meters and my depth of 2 meters, I'll probably stumble close to 11 cubic meters, right? So that's how you then come up with the dimensions of your sum, right? So my sump is going to be 2 meters deep, it's going to be 2 meters wide, and the length of that sump is going to be 3.32 meters, right? So one important takeaway here is this one, and it's important to understand the difference between QP and Q. Q is ADDWF, not peak wet weather flow, right? I've certainly made this mistake a lot of time. I've made these mistakes where you probably miscalculate your Q. And one thing that you'd realize that if you don't approximate your Q very well, you're probably going to get your VA as a negative. In most instances, if you've ever used this formula, like me when I was a rookie, I would always get my VA as a negative. And I start to ask myself, why is my VA as a negative? It simply means your pumping capacity is not enough to meet the dimensions of that sump, right? If ever you get a negative here, just know that your calculations are incorrect. It simply means your QP is not sufficient enough to function with the volume that you're getting. You mustn't get a negative there, right? So I believe that's the biggest takeaway that you have to be very, very, very careful of. This is your Q. Right. Now we've got design example number 2. Now, the size to be based. This is using the formula from Van Vuren, and if you check from a number of manuals, City of eThekwini, you have City of Ekurhuleni, you have the SALA manuals. I believe the CSIR manuals as well has this formula. It's quite easy and straightforward compared to the one that we used, right? So it's V is equals to T QP all over 4, right? So there are two variations of this formula, right? We have this one all over 4, then we also have all over 1,800 seconds, right? So they're just two variations of this formula. It's quite straightforward, it's quite easy. I also prefer using this one, though the other one also, they both work. So V, where V is the required wet well in cubic meters, then you've got your T, which is the minimum time in minutes for one pumping cycle. Remember, pumping cycle, it's coming back again. Then you've got your QP, which is the pump capacity in cubic meters per minute. I'm always emphasizing on being very careful when it comes to your units. Be very careful when it comes to your units, right? The maximum number of motor starts per hour shall be shown in this table, right? So this is what we're saying. Remember, the maximum starts per hour, right? It's 6. You're probably having a cycling time of 10 minutes. Remember, I always opt for 30 minutes so that I can have a maximum starts per hour of 2. I'm just trying to run away from that instance where we have to continuously switch on, switch off, switch on, switch on, switch off, right? So I'm trying to reduce the maximum cycling times per hour. This reduces the wear and tear of your pumping, of your pump station equipment as well, right? So this is the formula. So this is only exclusive to the guys that have signed up for the course. We're going to be going deeper into the example 2, just so that you guys can see the variations of how it's used, right? So this is the second example that you can learn as well. So it's quite easy, it's quite straightforward. And the good thing is with the table as well, it also shows you the approximate motor size. This doesn't do much for you, but it will just give you an idea of how much, like in terms of operational costs, right? Remember, whenever you do a wet well design, there's a part where you have to do a justification should your client require that, because sometimes when you're presenting a solution to a client, they might see it as too expensive. So sometimes you would have to justify that financially, like you have to do the numbers crunching. So this one will probably be easy, knowing that if I'm choosing a larger motor for my pumps, then I'm probably having a higher cycling time, minimum starts per hour. It's going to cost me this amount of electricity, and you do the mathematics. So like I said, this method is only exclusive to the paid subscribers, right? Now, that's that on the pump side, on the sump sizing. It's quite straightforward. There's a lot as well that we need to talk about, but that's just the basics of you sizing a wet well. So I've noticed that a lot of engineers are like, how do I size a wet well? Where do I even begin? That's what you do when you size a wet well, right? So that's that. So let me just quickly check to see if there are questions. Right. Let's start. The sump design equation is strictly for sump design only, or you can use it for the purposes of water. That's a good question. I would say this is strictly for sewer, because for water, it's a different scenario altogether. For water, you won't be having cycling times, right? This is for sewer, because we're strictly factoring in the concept of retention period. If you see, even in the formula, you've got the T value, which is the retention period. In water, you don't have any problems with the retention period. You have water that can stay in a reservoir for as long as possible, right? As long as it's being treated. But for sewer, we can't have a sewer where water can just be, the wastewater can just be stored in there. We're trying to run away from safety conditions. So yes, no, this equation cannot be used for water purposes, in my own understanding, right? What if the sucking machine fails after the maximum retention period? Yes, this does happen, Mr. Lance. Like, let's say there is the pump fails, right? Not the sucking machine as such, but let's just say your pump fails. What then happens? That's why we have what we call a detention pond, right? So generally, the retention point should be at least less than 6 hours, right? That's why even when you are sizing your emergency point, you are having that in mind to say, okay, we are talking about a maximum of 6 hours. So we always have an emergency point whenever we design our sumps, all the time. Just always know that, right? Particularly for a proper sump station, but not all the time, but you should always have it. Now, this is just standard practice. Another thing that you also need to know is whenever you're designing your pump station, you seldomly have one pump working, right? It's standard practice. You always have two pumps. One is on duty and the other one is on standby. That's because we're trying to run away from this issue of saying, okay, the pump is malfunctioning. What do we do? Then we start panicking. So there are certain instances where you do not have an emergency cone. You're just having that wet well because you do not have the leeway you don't have space, so to speak. Just like that example that we saw, you're in an urban area or you're in a flat area and you're in a flat area, you cannot have an emergency pond. So you'd rather have two pumps, possibly three, but three is pushing it. Two is a standard. One is on duty, the other one is on rest. So that when the other one fails, we start using the other one while we're fixing the other one. So it's standard practice. Never ever design a sump station with no two pumps or with one pump. It's at least one pump all the time, right? So what is the minimum and maximum allowable value to cater for freeboard? That's a very good question. I would say 0.5 meters. That's 0.5. Let's just go for 0.5. It's a flat value, right? 0.5 minimum. I wouldn't want to go all the way up to 1 meters for freeboard. So 0.5 is safe. Maybe minimum, let's go 0.3. So let's go from 0.3 to 0.5. From experience, I see that really works. What if two pumps are provided? One duty, one standby, instead of having emergency point? Yeah, that's actually the question that I was answering. Thank you so much, Wesley. That's a very that's actually a very good idea. So just use two pumps. So there are certain instances where we do not actually have to, we don't have, like I was saying, we don't have space to have an emergency point. But it's standard practice, depending on how big your development is and the circumstances of that that system that you're designing, you might need to have an emergency point. But if you can't have an emergency point, it's always standard to have at least one pump, right? Someone is saying, can you explain the difference between using the two formula when calculating the wet well capacity and when you should use the one over the other? Both formulas can be used, man. Both formulas can be used to calculate the same thing. And like I was saying, the other one is something that I'll probably be covering much in detail. I actually do not have the time to do it now, and it's something that we're going to be looking at exclusively when we do our conventional gravity sewers. But I've experimented with both formulas. They work. You more or less get to the same answer. Maybe there is a slight difference depending on the cues, because where you were probably likely to get a different answer is how you treat the cues. So remember, for my QP here, I hope you can see my screen. For my QP, I then says 1.43 multiplied by the peak wet weather flow. Someone might just go for the peak wet weather flow when they're using this other formula here. QP, they just go for the peak wet weather flow without factoring in that 1.43, which is your 30% stormwater increase, which is a lot, by the way, right? 30% is quite a lot, because you would have had factored that 15% in your peak wet weather flow. Then you have to factor in that 30% again, multiplying by that factor of 1.43. So it becomes a little bit too much, right? So this one, this one is my most preferred one, but I use both of them just to verify my answer to see if the answers that I'm getting are making sense. So I always like to use both of them. And I've got someone. Okay, someone is unmuted. Please mute your mic. Alex, please mute your mic. Thank you, thank you. We have Isaac, clarify on the manual and the name of the question. Clarify on the manual and the name of the equation for the example one. All right, so the manual that I've used, it's called the design, it's design guidelines neighborhood manual. It's just the design guidelines neighborhood manual, section K, which deals on sanitation, right? So if you just go to that manual, this particular equation is there. They do not, however, have an example in that particular manual. So the example is something that I did on the side by myself. But should you go to that manual, you can find it. Should you need that manual, please reach out to me after the webinar, and I'll be able to provide for you. So yeah, guys, let's quickly move on to the second section, which is your pump station. Right, let's talk about the pump sizing, right? So we spoke about the collecting basin, which is your sump. We've sized our wet well, right? Now we want to talk about the pump, right? How then do we move that wastewater from where it's being collected, which is your wet well, to the intended destination? So we have to talk about the pump, right? So we have to talk about the pump design. So the first one was this one, which uses what we call a self-priming pump, right? So this is when the pump is outside the wet well. This is where the pump is outside the wet well, as you can see, something like this. So you're having a separate pump house there, and it's actually operating. Then in this particular one, you're having a suction head, right? The suction head lift. You're going to see probably the example that we're going to do of sizing our pump. We're probably going to use this one. We're not going to use the submersible pumps. So this is the first option. Then you can have the second option, which is the submersible pumps. Now, from my experience working with a number of local municipalities, they do not like the submersible pump format. This one, it's mostly shunned on by a lot of municipalities, but you should just put it there, or maybe you can suggest it to the client. But most of them, they just like, no, we don't want this one, we want this one. So I've seen this one is popularly used, but this one also is something that I also like to use here and there, but most popularly used is this one. So we're probably going to be using this one for our example today. So the difference, as you can see, your pump is outside. For the submersible, your pump is immersed into your wastewater. So you have the pump inside the sump. It's a submersible pump, right? You have your pump inside. So this is the pump in this particular case. So having your pump, then you have got your discharge header, then that's going there, then that's pumping. So this is just your structural steel that is then used to hoist this pump. So let's say you want to remove this pump for maintenance. There's like a chain block here, right, that will be used. Then you can lift your pump, then it can be taken up for maintenance, and they can put another pump. So that's the structure here, right? So this is a submersible. This one is a self-priming pump. So that's probably one of the major differences that you're going to do. So we're going to be talking about this one, right? Our self-priming pumps, right? So the first thing that you're gonna have to do when you're sizing a pump is two things. It's two things that you need to know whenever you're sizing a pump. Let me just quickly write them down. You need your Q, which is the required flow, against your head, right? Right. You need your Q, which is the flow, against your head, which is actually, if we are being specific, it's called your TDH, which is your total dynamic head. So you need to first of all get your flow and get your total dynamic head. Those are the two parameters that you need to be able to size your pump. So we are going to briefly talk about sizing your pump in this section. Fortunately or unfortunately, I'm just going to be using figures that were calculated before. So the pumping configuration should be determined based on the analysis of pump flow versus the system curves, right? We're also going to briefly touch on that. So various combinations can be used, such as multiple pumps, combinations of small and large pump units, or variable speed pumps, or a combination of constant and variable speed pumps, right? So the first thing to determine is your Q, right? And then the required discharge in cubic meters. So what is our Q? We already got our Q, right? Remember when we're sizing our wet well, our Q is that QP that we have, right? So it's either it's your peak wet weather flow or it's your peak wet weather flow multiplied by the factor of 1.43, depending on what formula you're using, right? So we've already established where and how you get your Q, which is your cubic meters per hour. So this is the flow that has to be pumped, right, by that pump for this whole system to work accordingly, right? So what is the age? How do you then determine the age? So we said Q, we already have it. Then we have to talk about the pumping head calculation, which is your TTH. So this is the formula of calculating your pumping head. This is quite easy. Now, remember, we are using the self-priming pump, right? We are using the self-priming pump. So I'll explain both scenarios so that you can see why I'm using this formula. So your TDH, which is given by this formula, is probably your HA, which is your suction, plus your discharge, plus your F suction, plus your F discharge. Then we have got what we call the static height, which is the static head. So the static head, I'll start explaining from here. So let's just simply say, perhaps I have my wet well somewhere here, right? This is where I'm collecting my sewer. Then I've got my wastewater treatment plant, which is somewhere there. So the terrain is something like that, right? So this is at an elevation of 20 meters above the sea level. This is at an elevation of 37 meters above the sea level, right? So the static head is just simply Z2, right? Which this is elevation 2, this will be Z1. So your static height or your static head will be just Z2 minus Z1, which would be what? Which is 17 meters. That's not hard at all, right? So this is your pipe that's connecting the two, right? So your static head will be just the elevation of where we are taking the sewer, right, which is your wastewater treatment plant, to where the sewer is coming from. So Z2 minus C1, then you get your 17 meters. Then these guys now, where we're talking about your suction head and your discharge head, this is because we have, we're dealing with a self-priming pump, right? So let me explain quickly what that means, right? So your H1 suction, this is the secondary losses in the suction of the pipe. So what you need to understand that these H's, these are what we call head losses, right? So as you know from water hydraulics, whenever water is moving within a pipe, right, there is going to be that contact that water has with the walls of the pipe, right? That frictional loss, that frictional contact, or that contact results in friction, which results in head loss, right? So you will have to calculate that head loss. So we're going to have the head loss in the suction pipe because we are sucking that water from the wet well. So we have to calculate the head loss there. Then we're also going to have the head loss in the discharge pipe. right? Then we're also going to have the frictional head loss in the suction pipe, and then we're also going to have the frictional head loss in the discharge pipe. So it depends also on the manual that you use, but this is the very simplest formula that you can use. If you really want to go deep into this, you've got your static losses, then you've got your dynamic losses, right? But for now, we're just going to limit it to these, right? So you're having your frictional losses and you're having your head losses, right? So depending on the formula that you want to use, right? You can use the Darcy-Weisberg for your frictional losses. However, for this particular instances, I usually prefer using the Hazen-Williams. It's quite straightforward. It's quite straightforward. So I will just opt for the Hazen-Williams, though it's slightly less accurate compared to your Darcy-Weisberg, but it should suffice. I mean, you won't be off by a lot of meters. You probably maybe be off by 1 or 2 meters, right? But the accuracy in this particular case is not that much of a big deal. So the Hazen-Williams equation for calculating your head losses should work, right? So I'll probably use the Hazen-Williams. So what is the head loss in pipes, right? So that's the formula that you're going to use for the Hazen-Williams, where F is equals to 10.64. Then you have in your Q, which is your discharge, right? C is the roughness of the pipes, right? So if it's brand new pipes, if you're using HDPE pipes, we might use C as 140 or 150. So that's just the roughness of the pipes. We already have the Q, you raise it to the power of 1.5, then multiplied by D. D is now the diameter of the pipe. Now, one thing that you also have to notice is for your suction header pipe, right? This one, let me see if I can find the pipe. Yes, we're dealing with this one. Let me just maybe try and explain. Oops, sorry. I went very far. There you go. I'm here. So this is the suction pipe that we're talking about. This pipe here. This is the suction pipe. So first of all, we have got the head loss here, right? So we are sucking water from probably a distance. We're now giving it a hypothetical value of 2, right? So already we have 2 meters that we need to add there, right? Then we're having the discharge, right? What is the head loss here? Probably have that figure. Then let's say our treatment plant is there at an elevation of 37, and our pump station is at an elevation of 20 above sea level. So our static head is like what? As 17, right? That's the figure. Then after we do that, we also have to now calculate the frictional losses, because as this water is being sucked into the pipe, it's experiencing friction against the pipe walls, right? So this is where we also now get to use the Hazen-Williams. So the D now is the diameter of this pipe. Now I want you to take note, because the diameter of the suction header pipe is usually different from the diameter of the discharge pipe. The diameter of the suction header pipe can be 100 millimeters. We're still fine with this one. 100 millimeters, at least 100 millimeters. I usually use 100 millimeters, which should be fine. But for the discharge header pipe, we're saying we use a minimum of 160 millimeters diameter, especially if we're dealing with sewers. And B, if we're dealing with sewers, you do not have a discharge pipe that is less than 160 millimeters. Please take note of that. Anything smaller than 160 millimeters will give us problems, right? So you're having 2 plus 17, then you now calculate the losses in the suction header pipe, right? Using the Hazen-Williams formula that I just showed you, right? So what you then just do is you plug and play, you put your 100 millimeters there, then take note, we have got SG, which is the specific gravity. Now, we are dealing with sewer again. Now, if we're dealing with water, the specific gravity of water is 1, the SG of water is 1. But if we're dealing with sewer, right, this is now classified as a slurry, right? It's classified as a slurry, right? So which means your SG cannot be 1, right? Your SG cannot be 1. So probably you're using your SG of 1, 1.2, 1.3, 1.4. In worst case scenario, you can use 1.5, but 1.5 is stretching it. So anything from 1.2 to 1.4 can work for your SG. So you just plug and play, then you get your friction in meters, then you just add it on the total dynamic head. That's what you do. So you are going to have to calculate the friction for the suction, then you calculate the friction for the discharge, right? I hope that's clear, right? That should be easy. So one thing that you need to understand, this is for the metric equation, right? Now, somebody might be asking, I don't know if you noticed it, there is no L in this formula. So what you can do, instead of having 1 over D, you can put L there. This is the frictional losses per meter, right? Per meter of a pipe. So you need to put, after you calculate this value, you now multiply by the length of the pipe, right? I hope that doesn't confuse anyone. We just multiply by the length of a pipe, but your traditional Isaac-Williams equation, it usually just says L there, right? So this is the metric equation. So you also have to be very careful which equation that you use, because there's an imperial equation, right, that is predominantly used in Europe and some parts of America where it uses feet, but we are in Africa, we usually use meters. So make sure that you use the correct equation, which is the metric equation. So you just calculate your frictional losses, then you just multiply by the length of the pipe so that you can get the head losses due to friction for that pipe. So use that formula, you get it, you just plug and play there, you get your total dynamic head, right? So you need your total dynamic head. If you don't use your total dynamic head and you only use your static head, there is a chance that you might undersize your pump because you're using an incorrect TDH against maybe a correct Q, right? So remember, I said there are two components that you need to size your pump. You need your Q against your H, which is your TDH, right? So this will be in cubic meters per hour, right? That's your discharge. Q is in cubic meters per hour. Then your H is in meters. Those are the two components. So H, we're just calculating now, that's your TDH. You do that and you plug and play into that formula, then you calculate your TDH. Now, using those two values, you have to obtain what we call pump curves. This is where you have to obtain pump curves or a pump manual. So how do you obtain a pump manual? You obtain a pump manual from your supplier, from your local manufacturer, right? So here in South Africa, we've got a number of manufacturers that we have worked with. So this does not apply to every other country. So let's say you're in Kenya and you want to design a pump station, right? You have your QP there and you have your TDH. What you have to do is you have to find local pump suppliers within your country. Then you call them, you ask them, listen, we want a pump manual. They give you for free. You don't have to pay for this, right? So each manufacturer has got their own manuals that they use, or the pump catalogs that shows you what you call a system curve and a performance curve, right? So this is, I think this is Pump Africa, if I'm not mistaken. I usually use this for demonstration. So what you then see is you have got what we call a performance curves. They differ from manufacturer to manufacturer, but you would realize most of them, you're probably going to see something like this. So you open the manual, you're going to see a what? A performance curve. Now, what is this? Somebody might be asking themselves, these are pump models that they have. Like it's a model of a pump, right? Right. It's different from manufacturer to manufacturer. Like you see some manufacturers have pumps maybe that is written 4HH5P, some have got 2HPS, So they'll be having what we call their system curves like that. So what you then do is you get your system curve, right? You see that on your left-hand side, you are having your H, which is your TDH, right? Your total dynamic head. Then on the x-axis, maybe down here, I don't know if I should call it the x-axis, but on your x-axis, you should have your Q, right? It should be in cubic meters per hour. It should be in cubic meters per hour, right? So remember, we had calculated our Q that side, it was in liters per second, convert it to cubic meters per hour, then bring it this side. So you have your Q this on the x-axis, then you have your TDH on the y-axis. So what you do is you draw a straight line from your H, right, cutting right across that curve. Then you draw a vertical line, right, where these two intersect, right? As you can see, they intersect in that system curve there. So which means the pump model that we are going to select is 40/250. It's just a pump model, right? So after I do that, I go to what we call the performance curves, right? So these are performance curves that show you how does this pump perform, right? How does this pump perform? So you go to those performance curves, you do the same thing. So approximately for this example that I used, I think our TDH was approximately 82 meters, if I'm not mistaken, roughly around there. So you go to your performance curves, you do the same thing again. You're probably going to see lines like this. I'll explain what each line means, right? Then you do the same thing. You draw a straight line, and then you draw a straight line. So you go find your Q, and for this example, your Q was 60. Then you have your H, which is 82. Then when they intersect, that's your duty point. Now, let me just quickly explain this performance curve for you real quick. So these numbers that you're seeing here, it's different from each pump manufacturer. But if you understand and you listen this should help you understand any pump manual that you're going to come across, because the concept is still the same. So that's your performance, that's your efficiency. This is the efficiency of the pump. So as you can see, this pump is operating at 60.2%. This is not a very good efficiency. Usually, I like my pumps to operate at least 75% efficiency, but for the sake of demonstration, we see that this pump is operating at what? At 60.2%, roughly above 60.2%, roughly there, right? That's the efficiency of that pump. Where these two intersect is called the duty point, right? Now, these lines that you're seeing that are sloping this way, they're just showing what we call the impeller size, right? These are showing the impeller size, right? So for this particular one, we simply means we may need an impeller that is slightly greater than 260. So we might need to do what we call impeller trimming, right? So you can use what we call the affinity laws to actually find the exact size of an impeller. So the size of an impeller actually affects the function or the efficiency of your pump, right? So should you increase the impeller, but you are maintaining your system curve, you could actually get more flow in that. So that's your size of impeller. So this is the size of an impeller. That is the efficiency. Sorry about that. I'm back. I had lost you guys for a moment. So let me just quickly continue. Okay, so yes, that's the size of an impeller there. Then we're having the efficiency of that pump, right? So as you can see, that pump is slightly just below 60%, and the size of an impeller is probably slightly above 260 millimeters, right? So as you can see, you're still having your M, this side, which is your TDH in meters, and they're having your Q, right? So you now have the size of an impeller that you're having. You now have the model. Now what we now need is we now need to size the pump, the motor, right? So that was the pump. You have to understand that the pump and the motor are two different things, right? We have got what we call the pump house. That has got an impeller and a volute, which is just the pump casing. Then you've got the motor, which has got which actually runs the drive shaft, right? So you've got the motor, the one that you like collect on electricity and all that stuff. So we need to also size the motor, like how big is going to be the motor. So as you can see what you're having here with this pump manual, you're having your motor lines, right? These lines that are just going this way, these ones, right? These are your impeller sizes, right? So you just pick the impeller size that we have. We said our impeller size is at least 260, so we can go for 260 there. So what you do is you come here, as you can see, you're having your flow, you draw your straight line for the flow. We said our flow is 60 cubic meters. Then where that line cuts this line of an impeller, you draw a horizontal line. So that will be the size of your motor, right? So as you can see, that's 2, 4, 6, 8, 10. So the size of this motor that we might need for this pumping station to pump a flow of 60 cubic meters per hour over a TDH of 82 meters, we might need a motor of 22 kilowatts. Right, so that's how you size your motor. So you're writing these specs down. A motor of 22 kilowatts with an impeller size of at least 260. We're probably going to use affinity laws to find the exact size of the impeller, but let's go for 260. Right, so impeller size is 260. Your motor is 22 kilowatts. Right, then you're good to go. Then we come to what we call the NPSH, which is your net positive suction head. Now, this is very, very important, especially if you're dealing with a self-priming pump. Net positive suction head is important. So you need to find out what is the net positive suction head that is available for your pump. If you miss the net positive suction head, your pump will cavitate. Your pump will go into cavitation, what simply means that your pump won't function for more than 3 months, maybe 2 months. I'm not sure if you've ever been to a pump station before. If you've ever been to a pump station and you enter the pump house, and if you can touch the pump, I mean the voltage, if the pump is hot, it simply means that pump could be in cavitation, or if it's making a sound, right, that you don't understand, like a very loud sound, you know that that pump is also in cavitation. I'm going to quickly explain what that means. So the whole concept of cavitation comes from your net positive suction head, which is your NPSH there. So this is the reason why there's an R there, is the net positive suction head that is required by that pump. So for a 60, you extrapolate. So we are having our 60 there, you draw a straight line where it cuts that impeller diameter size of 260, then you go there. So you can see this is 2, probably this is 3. I'll probably approximate to say the net positive suction head that is required by this pump to function is 3.8. Right? So the next thing that you now have to do is you have to calculate what we call your net positive suction head available. What is the net positive suction head available? I'm just going to leave you with the formula and tell you how it works, but we're not going to do an example for the sake of time. This is something that we're going to go in deep in the course, right? So remember, we have got the net positive suction head required. Now, this is important, guys. Please pay attention, because this is where most people miss it, right? Like I was saying, if you oversize your pump, right? You're like, okay, let's just throw in a big pump there with a big motor and a big impeller size. What that means is that if you put a big impeller size, you're going to have a higher net positive suction head that is required by that pump. But now you have to compare the net positive suction head that is required by the pump against the net positive suction head that is available in your system, right? So if the net positive suction head that is required, right, is greater than the net positive suction head that is available, your pump will go into cavitation, right? Your pump will go into cavitation. So the questions that you might be asking yourself right now, how do I calculate, or how do I know what is the net positive suction head available? Now, the net positive suction head required, you can see you just get it from your from your pump gears, like how I'm showing you right now. So the next thing that you now need to do is make sure that you calculate your net positive suction head that is available. How do you calculate your net positive suction head that is available? So I've got 2 scenarios before I explain the concept of cavitation. I've got 2 scenarios. This is how you calculate your net positive suction head available, right? So we're having a suction lift. So this is the scenario that is mostly applicable to us, right? Because we are sucking water, or we're sucking our wastewater. So we're having our pump that is in that configuration, and you're having your sump that is like that, right? So this is where there's an open air, right? So your net positive suction head is given by PP, which is your atmospheric pressure or your barometric pressure. Then you're having your LS, right, which is the suction lift. So if it's 2 meters, you're having there. Then you're having your VP, which is the vapor pressure of the liquid, right, of the sewage. I'm sure you can get these values. Then you're using your HF, which is your frictional loss in the suction pipe. So we did speak about the HF. You can quickly use your Hazen-Williams and quickly calculate, okay, what is the length of the pipe, what is the diameter, and then you plug and play, you get your HF. It's usually a very small value, maybe 0.5. Then your vapor pressure, you know what your vapor pressure is. Where are you in the world? Just quickly calculate your vapor pressure. Just so you guys know, the vapor pressure in South Africa is different from the vapor pressure in Kenya because of our different altitudes, height above the sea level. So get your vapor pressure where you are. Then what is the LS? You have the LS. What is that length from the top of your liquid of your wastewater to the center line of your pump, right? That's your LS. So if it's 2 meters, then that's that. Then what is your barometric pressure, right? So let's say these values, you can quickly get them, like what we're just discussing. Your LS, you have it. Your vapor pressure, you can get it. Your PPH, you can get it. What is that barometric pressure at that particular point? And then the only thing that you might need to calculate there is your HF, which I just showed you the formula of how to calculate your HF. So this is important. After you calculate your NA, right? Let's say the net positive suction head that is available is 2.8, right? This is just a number, right? So if your net positive suction head that is available in your system, right, is 2.8, but according to what we said here, according to what we said, or according to our pump manuals, right, and the TDH that we selected and the H and the Q that we selected, we are saying that the net positive suction that is required by this pump is 3.8, but the net positive suction head that you have is 2.8. So what this means is the net positive suction head that is required is greater than the net positive suction head that is available, which means your pump will cavitate. It'll cause cavitation. Unfortunately, I don't have pictures to show you what a pump in cavitation looks like. So cavitation is a simple phenomenon where we are simply saying the vapor pressures, they form on the eye of an impeller, right? Then they implode, causing the damage of the impeller. So with time, because of the bursting vapor bubbles on the eye of the impeller, it damages the impeller. So which means with time, what will happen is that your pump will become less and less and less and less efficient. So instead of it pumping 60 cubic meters per hour, you'd realize that in 2-3 months, it's not even pumping 50 or 60 cubic meters per hour. It has dropped down to like 30 cubic meters per hour because your impeller is being damaged by this concept of cavitation. Now, if there's one thing that you're going to take seriously, please take this and take this very seriously. It's very important, particularly if you're dealing with these types of pumps when you are having a self-priming pump. So just a recap. Remember, you have to calculate your LS. It will be here, right? Then you would have to calculate your, right? So LS will be probably here. So from the center line of your, right? So let's say your liquid will probably be at that level. So from the center line of your pump, right? That will be your LS, right? So remember, this is a closed system. So which means if you are using the formula, you're using this formula, right? With a closed suction supply lift. Definitely. So you're having your PP, right, which is your absolute tank pressure, minus your LS, minus your vapor pressure, and minus your HF. I wish I could explain the concept of cavitation to you guys, but I can't. But just know that if somebody is saying, what is cavitation? Just say, this is a scenario where the net positive suction head available is less than the net positive suction head that is required for that pump to function. Then your pump will be in cavitation. It will definitely be damaged, right? So you would see that in that equation, net positive suction head available, you've got the HF, and your HF is also related to what? To the diameter of the pipe. So should you increase the diameter of the pipe, you probably decrease HF. And should you reduce the diameter of the pipe, you also increase HF. So I'm just telling you this relationship so that you can know what to adjust should you have a net positive suction head that is less than the net positive suction head that is required. So in that particular scenario, it says that you have to lessen the depth of your sump, right? So that your sump doesn't have to suck deeper, so that you don't have to have cavitation, right? So cavitation is a big problem in pumps. I'm telling you, this cavitation is a silent killer of pumps. It's a serious issue. So whenever you're having self-priming pumps, you need to take this issue of calculating cavitation very seriously. Failure to do so, like remember, this is actually a sewer pump station. If it's potable water, we understand, right? If a pump fails, we can afford to go for 24 to 48 hours while we're trying to fix it. But for a sewer pump station, every hour is valuable. So the pump station has to be mechanically robust. You can't design something that fails after 3 months. And I'm telling you this now from experience. It's because of the improper sizing of your pumps, which then causes them to cavitate. And one of the silent killers is you ignoring things like calculating this calculation that we just did now, right? So just take note of that. I had to really explain that. So if there's anything that you can take out from the webinar, just know that whenever you're dealing with your self-priming pumps, the number one thing that you need to watch out for is your cavitation, right? Okay, so I think that's that. Now, from the pump station, I think that's it. So what you then do is you have the size of your motor, right? you have the size of your impeller, right? And then you find out with the size of your motor and the size of your impeller, what is the net positive suction head. If you see that your pump is not cavitating, then you're good. So you then talk to your supplier, say, okay, listen, I want this pump with this impeller and this motor. Then they will probably supply the proper pump with the proper volute and everything. So all you need is those two parameters to just size your impeller and size your motor and check your net positive suction head that is required. Then everything else your manufacturer should be able to supply for you. So this is not something that is done by the mechanical guys, because the mechanical guys, they won't have the due diligence to then calculate and investigate the net positive suction head phenomenon. They won't do that. They will just say, okay, what's our Q? What's our H? Okay, cool. This is the pump. Use this one. But if you then don't check what is the net positive suction head for that particular pump, what is the net positive suction head that is required by that pump that they selected, and what do you have on the ground if you compare the two. And if it's not cavitating, then you're good. But if it's cavitating, if you don't make that investigation, then best be guaranteed that your pump station or your pump will fail due to cavitation. So that's very important, right? So I just said to cover that. I'm not going to talk about the types of the impellers. Obviously, this is a type of a slurry pump, right? So the pump that you're then using for pumping your sewer is slightly different from the pump that you're using to pumping your potable water because of the differences in your SG, right? The specific gravity. Here, this is regarded as slurry. So you need a specific type of an impeller. This is what you also have to specify to your manufacturer. You tell them these are the specs. I'm pumping sewage. This is the SG that I'm expecting. And they give you the catalog. Okay, this is the type of impeller that we're going to use. It mustn't have too many vents, by the way. And the material that you're using for the impeller is also different from the material that you use for water. So let me just quickly move very fast. I'm running out of time. Then we have the pipeline design, which is usually the last bit of our pump station. So this is just an example of a pipeline design. This is done in IDAS, right? I'm not so sure if you guys know the software called IDAS. So it should be able to give you a data pen set like this, where you're having a distance, your ground level, invert level, your depth. So for this pipeline, usually the minimum depth should be about 0.6 meters, right? In less trafficked areas. But in trafficked areas, we're talking about a maximum of 0.9 meters to 1 meter below the ground. So only in trafficked areas should you have that depth, right? Then you're having your grade, right? Then you're having your static head, your dynamic, and your flow, and all these other things, right? So I'm not really going to talk about how to calculate to ensure that. I'm just going to talk about the design criteria that you need. So we're going to cover the functional design consideration. The first one is your pump pipe compatibility. Now, this is investigated by doing what we call a system curve. So unfortunately as well, I'm not going to talk about that, but just know that you have to also check, does the diameter of your pipe correlate with the discharge that is being released by your pump. So you just don't plug in any type of pipe, I mean, any diameter of pipe there, right? So we said it's a minimum of 160 going up, right? So probably your 160 may not be compatible with a discharge of 60 cubic meters per hour. So please do look that up. Just make sure that you look about 16 curves. You should be able to find something along those lines. But I just had to bring it up because sometimes people will be like, okay, let's just use a pipeline of 200. They just plug it in there and then like this work. Is it compatible with the flows that are being released by your pump, right? Then we also have got what we call the soft cleansing velocity, right? In as much as this is a pressurized system, you have got a minimum velocity that is required in your pipeline or the rising main. So the minimum velocity should be from 0.75 to 1 meters per second. This is to prevent solids to settle. So any sedimentation of solids is not required. Then the maximum velocity should be at least 3 meters per second. Anything above 3 meters per second will not only cause the wear and tear of the pipes, but it will also cause sedimentation in the opposite direction, in the sense that you know that yes, your sewer is 90% fluid, but there is those small particles that will still be suspended particles. So you don't want your water to be moving at a faster rate that it is now leaving the particles behind, if you get my point, right? So the suspended solids, they need to be in sync with the water that you're pumping. So anything above 3 meters per second will also have caused that issue of sedimentation of solids in your pipes. Now, we have got the air management. So you know, every time you're having a pipeline and you're pumping it, we always have to ensure that we install air valves. So install air valves on all summits in your pipe. Install air valve on all summits in your pipes, right? To prevent airlock as well, right? Then we have got surge control, right? So sewer rising mains are sensitive to water hammer during sudden pump starts and stops, right? So you need to use what we call surge arresters or non-slam check valves. Now, surge control is important, particularly whenever you introduce a pump in the system is important, especially for your sewers, right? Where you are going to be, remember we said we were designing our sump, we are having a maximum number of starts and stops. So that's very important and you need to take note of that. So that is very important. But I would also want to qualify to say for any pipe diameter that is less than 300 millimeters, surge control is not that much of a big deal, right? For any pipe diameter that is less than 300 millimeters, you shouldn't worry too much about surge control, but just it's something that to think about. So to model your surge control, you can use what we call Bentley hammer. It can show you your surge analysis. Then we're also talking about retention time. So we also spoke about retention time in our wet well ponds. You also have to talk about retention time in our pipelines as well. So we have got a minimum of 6 hours to avoid septic tanks. I think we spoke about this, right? Then we're going to talk about physical designs. This should be very, very easy. We're talking about your pipe material. We have got a wide range of pipes that you can use. You can use HDPE or UPVC, but only heavy duty, or you can use ductile iron, but it has to have what we call an epoxy lining, right? However, HDPE is preferred for flexibility, durability, and surge absorption, right? Now, pipe diameter, recommended minimum is 160 millimeters, right? So large diameters reduce friction, but can increase settling of solids. So you also need a balance. So the bigger you get, you know that your velocity from the continuity equation, Q is equals to VA. So the more I increase my V, right, it affects my A. So the velocity is inversely proportional to your area. But if you increase your pipe diameter, then you also increase the pressure, then reducing your frictional losses. But at the same time, that might increase your cycling problem. So remember, don't oversize things. You size the correct size of what you need to use, particularly if you're using anything that has to do with water and wastewater management. You need to size your infrastructure. Never oversize. You will have problems. So minimum cover 600 millimeters in non-trafficked areas. Maximum cover should be maximum there. Should be 900 millimeters in road reserve or vehicular zones, right? Then we also have to talk about bends and anchors. So I'm just quickly mentioning this. Sometimes you can do your hydraulic analysis of your pipe, right? And you're having your flow and your velocity, everything is working just fine. But if you don't do the proper physical design, it's bound to fail. So there are things that are called anchors. So you always have to design for anchor blocks that are then placed at all bends and all T's and all valves and all dead ends. You always have to have what we call an anchor block. It anchors your pipe because as your water is moving inside the pipe, it imposes hydrostatic pressure on the external pipe, right? So your pipe has got a tendency of moving if it's not anchored, because you have to understand that this water is moving at a faster rate. Né? So if it's moving at a high speed velocity, like for instance, you're having your pipe, then there is a bend there, right? So if water is moving in that direction, let's say at 2 meters per second, it will hit the walls of this pipe at this particular place here, right? So there's a tendency of your pipe to move in that direction, right? So in these particular places, wherever you are having bends, you have anchors so that it's anchored in that particular place and it doesn't move to the left or to the right. Right, so anchors are quite important. So just to generalize it, all bends, T's, valves, and dead ends, you must always place your anchor blocks. Then the issue of isolating valves. I'll just quickly show you guys in the next slide, right? This is the configuration that you might need, particularly for your pump station. So just as you can see, this is your self-running pump. As you're coming out of there, you always need what you call a non-return valve, because whenever you're having a pump, right, you have to ensure that there is no backflow. Right, so we have a non-return valve. That's the first thing that we have. So we'll probably have a non-return valve, as you can see. After we have a non-return valve, we have a gate valve. After we have a gate valve, we then have an air valve. So those are three most important valves that you need. I usually like to place my air valve outside the pump station, because sometimes when the air valve is operational, there's some water that comes out of the air valve. And if you put it inside your pump station where there's electrical equipment, you might cause some electrocution there. So I just standard practice, just try and place your air valve outside your pump station and have it function from there. But inside the pump station, just immediately after your pump, place your non-return valve and then your gate valve, and then you can place your air valve just outside. Then we already spoke about thrust block. Every time we're having bends, always put your thrust block, right? Right, guys, I think that's more about it. I'm sorry I had to rush quickly at the end there. So can I just quickly take 5 minutes of your time? We are 3 minutes ahead of time. I just want to quickly maybe check for a few questions in the chat box before I conclude the meeting, right? I just want to quickly check some questions in the chat box, right? Now, somebody, sorry, Asavela, I hope I pronounce your name very well, says if net positive suction head available is less than the net positive suction head required, what is the best solution? Do we reduce the suction lift or increase the suction lift and the pipe diameter? I like that reasoning. Yes, we can, let's reduce the suction lift, right? So we'd rather reduce the suction lift. That's the first thing. That's the most immediate solution. Or what we can do is we can change the impeller diameter. Right, we can just literally change the pipe, right? We can literally change the pipe. We can literally, sorry, not the pipe, the pump. Sorry, so we can resize the pump, right? So the immediate one, try to play around with your suction head lift. I think that's the most easiest one that you can do. Just reduce the distance that your pump has to suck water from the sump. So you just reduce your sump depth. So you might have to resize your sump. So yeah, that's a very good question. I did the sanitary sewer course earlier. The sewer pump station was not offered. Yeah, it was not offered because that one is a strictly gravity sanitary sewer. But this one was just going to finish up that other section of pump station design, right? So that's slightly different this time. Should we consider that setup as closed even if there is an event? I'm not so sure about that one. Can you please give me more context? Let's go to Abrahams. Can you use the same formula for TDH when you have submersible pumps, given there is no suction pipe going in, or is the equation specific to the same? Yeah, I think that's a good question. So if we're using submersible pump, there's no need for us to use that equation because you don't have the suction head relief, right? So use that same equation for submersible pumps, but do you have a suction head? No, you don't. So that's zero, right? So because you don't have a suction head, what you're going to realize that what you'll be left with is your discharge head, right? So you still use that same equation, it's applicable, but do you have the suction lift? No, you don't have, so you just put zero there. Okay, so it's still very much applicable. Still, that's a good question. Someone says, for economic reasons, can you have two pumps in parallel arrangement to meet the sewer flow? Yeah, I can tell that's a very good technical question. You know your pumps very well. So what is the effect of putting two pumps in parallel? The effect of putting two pumps in parallel, right, is to increase flow, right? And the effect of putting two pumps in series is to increase the head, right? Now, if I'm having two pumps, I don't think it's more economic rather than having one pump, right? So what you can literally do is you can actually see, we can do two pumps, right? that are quite small, then can work at the same time to meet our discharge that we want. That could work, right? But imagine then having two pumps that you are consistently switching on and on, off, switching on and off, switching on and off, right? So in that regard, I'm more worried about your operation and management. But this particular reason, I would probably use it when maybe we're dealing with potable water, right? When we're just pumping water in, we want to increase our flow in the system. So I would rather have them in the parallel arrangement. But for the sewer flow, I would not recommend it. I would not recommend it. I would rather recommend one big pump and have one on the standby that can just function quite well. What if the septic condition, okay, how will formation of hydrogen sulfide be catered for in the design? That's what I'm saying. We have to ensure that we don't get septic conditions, right? How do we not get septic conditions? We have to ensure that we maintain our cycling times of 30 minutes. If you're doing 30 minutes, which is your maximum of 2 starts per hour, right? So the septic conditions, you only ensure that they do not occur if you stick to your cycling times. Ensure that you don't you don't pass the maximum of 30 minutes of containing the sewer in the sump, right? Especially in, now here's the thing, I think that's a good question. Especially in hot climatic regions, septic conditions, they tend to occur quickly, right? The heat will speed up that anaerobic reaction, right? That will produce your hydrogen sulfide gases. So I would say let's ensure that we stick to our cycling times, and let's be strict on that when it comes to septic conditions, right? So it's also important, that's what I was saying as well. It's also important, particularly in the sewer, to always have one standby pump, just in case if the other one fails, we cannot afford to collect sewer, especially in areas where we don't have an emergency pond, right? Especially in areas where we don't have an emergency pond, right? So yeah, I think I've tried to answer as much questions as I can. So this was more of a sump design introduction. Obviously, there is a lot more to be covered and there's a lot more to be learned, particularly the best standard practices in the placement of your sump. How do you place your sump? Where do you place your sump and all that stuff? So here's the thing, this recording will be provided for you guys. As long as you're part of our community, the recording will be provided. Should you also need the notes, because I was presenting a lot of equations, there's a PPT that will be sent as well for references so that you can start on it, right? So this is an introduction. This is by no means an exhaustion of what we're doing. We're going to do more webinars like this. Maybe let's say next time we're just going to be drilling deep into the pump station or into the pump sizing only. You understand? This is more of an introduction for you guys to have an overview of what a pump station entails and what are the components that are involved in a pump station. So guys, thank you so much for attending. Just one more announcement. We are having our sanitary sewer course that is coming up on the 30th of June. If you haven't signed up, please ensure that you sign up. I'll just drop the link into the chat box. Ensure that you sign up. And just, if you still have questions, I am part of the Rose Up community. I'm sure you should be able to get my number. Let me type my number in the chat box. You can reach out to me via WhatsApp and we can continue the discussion. I do not want to drag this meeting any longer. I'll be in trouble if I keep you guys here. So it's already 10 past 9 according to my time. I don't know where you're joining us from, so I don't want to keep you late. So you can quickly click that link and then you can sign up for the course. We're probably going to reach out. Should you also need to sign up for the course, there's my number. If you've got more questions as well, there's my number. I'm there on WhatsApp. You can just quickly slide into my DMs and we can continue this conversation. All right, guys. Thank you so much for supporting us. Thank you so much for coming. I really appreciate you. The meeting is adjourned. Have a good night. Bye.